Welcome to my video course on Communications-Based Train Control, CBTC. If you've ever stood on a jam-packed metro platform during rush hour and you're just wondering, why they can't simply run these trains closer together to clear out the crowds, well, you are about to discover the exact engineering answer to that question. Today, we're exploring a massive paradigm shift in railway signaling. We are literally moving away from century-old, rigid physical track divisions, and we're stepping into a world of continuous, high-speed radio communication that dynamically adjusts safety zones in real time. And this isn't just about safety, it's about extracting every single ounce of capacity out of our transit networks.
Okay, let's dive into this. Here's our syllabus for today's explainer. First, the fixed block problem. Second, moving block systems. Third, the safe braking model. Fourth, dynamic separation. And finally, number 5, limit of movement authority.
Starting right off with Section 1, the fixed block problem.
So to really appreciate the genius of CBTC, we first have to understand the baseline legacy systems that it's replacing. For decades, railways have controlled train separation by dividing the physical tracks into static segments. We call these blocks. Just take a look at the blue line under Train 1 here. In a fixed block system, the network doesn't actually know exactly where the train is within that block. It only knows that the block itself is occupied. Because of this lack of precision, the system has to assume the absolute worst-case scenario. It claims the entire physical block for that single train. Plus, these blocks are sized for a train traveling at maximum line speed, which requires this massive safety distance. This creates a tremendous amount of wasted space right behind the train. Train 2 literally cannot enter Block 2 until Train 1 completely clears that previous block. It's safe, sure, but it is highly inefficient.
Which brings us to Section 2, moving block systems. So how do we solve this bottleneck and utilize all that wasted space without compromising safety? And this brilliantly illustrates the exact moment the paradigm shifts. Notice how the protective zone is no longer tied to the physical track infrastructure itself. Instead, the block dynamically moves with the train. That red braking curve you're seeing, it isn't based on some arbitrary track section anymore. It's trailing precisely behind the confirmed rear location of Train 1. So by constantly transmitting its exact position via radio, Train 1 allows Train 2 to run much closer, safely utilizing what used to be entirely wasted track space.
Let's lock this concept in by juxtaposing the two philosophies here. Fixed blocks are rigid. They rely on a static speed profile and this artificial separation based on maximum line speeds, which basically means your incredibly expensive track infrastructure is never fully utilized. Moving blocks, on the other hand, the absolute foundation of CBTC, are fluid. They use a dynamic speed profile and calculate the absolute bare minimal safe separation required. The end result? You extract the maximum possible capacity out of your track design, you push more trains, you move more people, and you drastically reduce passenger wait times. It's a real game changer.
Moving right along to Section 3, the safe braking model. Conceptually, moving blocks sound fantastic, right? But how do we actually ensure these multi-ton machines don't collide when their safety zones are just shifting around in real time? Now, what's really interesting about this slide is how we can look at the 3 different speed profiles on the left to see the actual math that's keeping everyone safe. A train traveling at 120 kilometers per hour requires a vastly different stopping distance than a train crawling at 60. In a CBTC system, the braking curve isn't some one-size-fits-all guess. The stopping distance is dynamically calculated based on current speed, track grading, and crucially, the exact confirmed position of the preceding train. As the train speed changes, that braking curve adjusts instantly. Let's walk through the exact chronological sequence the CBTC system actually executes to guarantee this real-time safety. First up, the train-borne system determines its own location with extremely high precision, and this is entirely independent of traditional track circuits. Second, it continuously beams that location along with its current speed and direction right to the wayside controller via radio. Third, based on this constant stream of data, the system calculates the dynamic safe braking curve. This entire loop happens continuously, ensuring that the mathematical safety net is never more than a fraction of a second out of date. On to Section 4, dynamic separation. Building directly on that braking model we just talked about, we can look at train spacing and see exactly how CBTC impacts overall railway throughput. I want you to think of dynamic separation kind of like a protective invisible bubble surrounding the train. Now, in legacy systems, this bubble was essentially made of concrete. It was a fixed size no matter what was happening. But in CBTC, this bubble breathes.
When the train accelerates to high speeds, the bubble expands, pushing the safe stopping distance further out to account for all that momentum. As the train slows down to pull into a station, the bubble shrinks tighter on the train. So by enforcing only the bare minimum safe distance needed for the current exact speed, trains can safely bunch up right behind one another during those slow station approaches.
And finally, Section 5, Limit of Movement Authority.
All right, so we know where the trains are, and we know exactly how long it takes them to brake. But how does the system physically authorize a train to actually move forward? Well, for over a century, a train driver's authority to move forward came from looking out the window at physical green, yellow, or red lights. The Limit of Movement Authority, or LMA for short, completely replaces those physical signals. Using the continuous two-way data we've been discussing, the system gives the train a precise, ever-updating target stopping point directly on its onboard computer. The train is authorized to travel safely up to that specific coordinate, the LMA, which always sits safely behind the nearest obstacle ahead.
Let's move to and see how this builds into a complete architectural loop. We can look at how three major subsystems are in constant dialogue to calculate that movement authority. First, the train-borne system is constantly reporting its status. This data flows right through the DCS, the Data Communication System, which is essentially the secure, highly redundant wireless network of the railway. The DCS delivers this directly to the wayside system, specifically the zone controller. Now, the zone controller looks at the whole board, calculates the LMA for every single train, and then sends that authority right back through the DCS to the train. It's just a continuous, closed-loop conversation.
But what actually dictates that stopping point? What are the absolute hard stops in the system's logic that restrict a train's movement authority? Well, to ensure fail-safe operations, the system will always cap an LMA at the most restrictive of several different factors. The most common one is just the rear of a preceding CBTC train. But the LMA will also clamp down if it detects a track section occupied by a failed or non-communicating train. It'll also restrict movement at the physical end of the track, or, at the entrance to an interlocking area if the route hasn't been properly locked and secured. In this system, safety is absolute.
So, by shedding the physical limitations of fixed blocks and fully embracing continuous radio communication, CBTC doesn't just make railways safer, it extracts the absolute maximum efficiency from our infrastructure, really paving the way for the high-density, automated transit networks of the future. Thanks, we can see you next video.